Hey, and good morning. So both Adam and I work on the app security intelligence team at Lookout Mobile Security. So if you wanted to find out everything about a person, would you really still want to skim data off of their PC or their Mac? I mean, in all seriousness, your phone has 2 cameras, 2 or more microphones. It has a GPS receiver. It comes to you into every business meeting, and it's sitting by your bedside when you go to sleep. As far as I'm concerned, that's the juiciest target that there is. Maybe I'll switch to the next slide, or there we go. So I think we are all aware that we are making some privacy trade-offs in return for free apps or free information. So this is a probably somewhat incomplete list of all of the information on your phone. I tried to sort it in order of increasing intrusiveness, but that's somewhat subjective, I suppose. And we all have some kind of threshold where we don't want an advertiser or any app developer to know about that data. So take a second or two and think about where you would draw the line here for yourself. We'll get back to this slide later, but for the moment, let me switch gears and talk about how personal data is accessed on mobile devices. Oh, thank you. So I'll talk about Android because it's a system I'm most familiar with. As most of you know, Android uses the Linux kernel and with some extensions, and it also uses its security model, but it kind of turns it upside down. UIDs are usually associated with a user on a Linux system. On Android, they are associated with an app. As you can see here, every app on the device, I hope this is readable, has its own private directory that is under its own UID, and other apps can't read what's in there by default. So for some reason, pesky app developers actually want access to some personal data. I'm not sure why, but they want to offer location-based services. They want to actually do things like help you edit your pictures or any such things. So Google built a number of ways to do stuff like that into the Android system. So there are some APIs for this. Some things are done via the file system. Again, this is probably a somewhat incomplete list up there. So these things are controlled via permissions, which are mostly implemented as Unix groups on Android, and you can see here a listing of some files in the dev file system on a Nexus 5X, and you can see how the groups determine access to them. So obviously, every one of you checks every permission of every app you install on your device. Of course, yes. I think the vast majority of people does not. So thus far, I've been talking about access as intended. What happens if the device actually gets compromised? So as you might have expected, all of those nice restrictions go out the window. We can directly read all of the SQLite databases if a device is rooted. And just to show that point, I demonstrated how not complicated it would be to read, say, WhatsApp data, the WhatsApp database, and look at all of the messages in there. So all of the end-to-end encryption in the world is not going to save you if your device is compromised. And again, I'm sure all of your phones get updates directly from Google the day after they come out. I'll leave that one for you to figure out. So where do we stand on the exposure of personal data at this point? So without root access, just due to permissions, all of the things in bold can be accessed. And I think this really drives home the point that, that we need to be very, very careful about what permissions allow on devices and what capabilities there are in each app. And also, if you remember the line that you drew earlier, I'm pretty sure there are some that are beyond the line here. Once the device is rooted, as expected, absolutely everything is open, and a whole bunch of things that are not even on this list, such as Wi-Fi passwords, authentication tokens, and so on. So on that note, let's look at our first example of an app that is just a little bit too curious. So Ejectsin is an ad SDK that was present in literally hundreds of apps on Google Play. Cumulative download was over 100 million times. And in February, Adam was investigating an app for completely unrelated reasons and noticed some suspicious activity.
So here's our sort of suspicious activity. So here's our sort of suspicious activity. This is something I saw in a packet capture, and it's some type of binary payload getting downloaded over HTTP. It's an unknown file format. It's likely an encrypted file. So we see this sort of traffic from malware obfuscating malicious payloads, but it doesn't necessarily mean much. The main question here is, what's the app doing with these files? And here's what I found when I looked. They're jar files, and what's generating the request is an SDK. It's bundled in tens of thousands of apps. What's on display there is instantiation of the DEX class loader. Not pictured here, the jars are XOR encrypted, and the multi-byte key is included with the download URL, which is sent from a REST API that the SDK communicates with. So you can see from the code sample that decrypted copies get deleted from the disk after load. The next step in looking at this was to decrypt payloads and see if they had anything interesting in them. There's lots of ways to do this. Here's the one that I used and that I often tend to use. I like to replace DEX-to-OAT on a newer Android system with a shell script. And this just dumps any loaded jar or APK files to external storage. I wouldn't necessarily recommend this approach. There are generally cleaner ways to do this. But it does work, and I got quite a few jar files to look at. Here's what I'd consider to be the payload of special interest. And what this does is it registers a phone state listener that logs all incoming calls, duration and phone number. And then this call log data gets uploaded through a REST API call. So we can see sort of malicious behavior at this point, that this SDK doesn't disclose that it does this sort of thing. But let's step back for a moment and take a look at the network traffic with a couple of goals in mind. One would be to confirm traffic with phone numbers is actually going back to the C2, that the numbers are actually able to be read. And also, we'd like to be able to view the traffic from the API and make sure that our understanding of the plug-and load process is actually accurate. So in terms of how the plug-and load process works, the SDK sends out SDK config requests. The server responds with responses that'll have encrypted jar file URLs and AES or XOR keys for decryption. Plugins get downloaded, the plugin code gets loaded. There's a time delay, then business intelligence data gets uploaded. That's call logs, but also location information, lists of installed apps, things like that. So fortunately, the API traffic is mostly pretty easy to deal with. Traffic's base 64 encoded. And then when it's decoded, the first 16 bytes are an MD5 checksum for the message body. And then the message body is just gzip compressed JSON. So it's fairly straightforward to write a PCAP parser to process those. And there's the plain text on the slide there. Here's a look at the call log uploads. Payloads base64 encoded, pipe separated data. BI type 22 is call logs. And base64 decoded, that looks like this. It is field 5 that contains the phone number, and that's again base64 encoded and RC4 encrypted. Half the key is in the message in one of the fields, and the other half is just hard-coded into the app. So this is enough to actually decrypt phone numbers and actually view them. So that's what a key looks like, and we can see that we can take a phone number now and decrypt it. So that covers maybe 2/3 of the apps. Newer SDK versions, encryption is altered to be quite a bit more sophisticated. All the code was moved out into a native library. And payloads are AES encrypted using a randomly generated key. And then in the HTTP header, the key is sent, but it's RSA encrypted with a public key that gets bundled with the app. So the way to deal with these payloads is that we need to dump them from memory, and you can see an example of that on the slide as well. It's probably good to keep in mind that it's difficult for an app to keep secrets from another privileged app on a device. And we'll come back to that a bit more when we talk about targeted surveillanceware. So ultimately, we were able to work with Google and some of the other vendors and get hundreds of apps either removed or updated in the Play Store. For what it's worth, the SDK vendor has made some statements after this started getting press coverage that they weren't actively using the decrypted data. Whether you believe this or not, what the vendor is doing at the moment is probably not the only privacy concern here. So from here, we're going to talk about purpose-built surveillanceware.
Thank you. So the motivation of advertisers for spying on you is usually to sell you more stuff. So the next set of apps we are going to look at is usually installed with a much less benign intent to actually purposely spy on you and find out interesting information. So these are the screenshots of the web pages of some vendors of commercial surveillanceware, if you will, the bucket of deplorables. And as you can see, there's absolutely no shortage of these apps. They tend to be used by jealous romantic partners, maybe people who want to blackmail you, or very overly curious employers. The creators of these apps are usually fully aware of the unsavory nature of what they are doing, so they kind of try to hide the intent somewhat, and or some of them do anyway, try to sell the apps as theft protection apps or backup. I'm not sure how exactly they managed to swing that, or child protection apps.
So here we've got an example of this type of app. It's called Mobile Recorder. And discovering these apps is quite a bit easier than something like a misbehaving ad SDK, because they have websites like this. They advertise very publicly. So this says it's the best app for tracking spouse, child, or employees. That's probably not true. It's not particularly well implemented, but it does do what it says it does. Let's take a short look at the app's capabilities, and we'll see how it's structured. So this type of surveillanceware pretty much always requires physical access to a device to deploy. This one doesn't use any capabilities which need root, which is fairly typical. Some of the apps will provide sort of expanded functionality if they're installed on a rooted device, but usually this sort of thing is never bundled with exploits. This particular app is fairly small and easy to understand. On launch, it sets up some content observers to monitor call logs and SMS messages. And then it creates a number of services which get sent broadcast messages either on a schedule or in response to certain events. So here's a rundown of some of the services where the core features are implemented. You can see on the slide there they all use standard Android APIs. And here's a listing of some of the other more interesting capabilities. One thing that's sort of note is that this app does try to intercept notifications, which is a reasonable way to get data to third-party apps without actually having root. Another thing that might be interesting is mobile data or Wi-Fi toggle. It's probably offered because it might be required to upload data back to a C2. So this is just the SMS content observer on the screen. One thing of note, it also parses inbound commands. Typically, these types of apps will only offer hiding functionality to hide their icons. So there's going to be places in a device UI where the app is still visible, but the user is just less likely to notice that it's on a device. This app offers two control channels, SMS and HTTP. SMS commands just get identified through a magic string, and HTTP commands are received just through polling an endpoint. Data upload doesn't use any special encoding. It's just either a serialized hash map, serialized to JSON, or file uploads like images are uploaded as multi-part form data, so standard file upload. This app does offer configuration to limit data usage. So we got a couple of apps taken down from the Play Store. And you can see that now that the vendor's been caught, their website's been updated to promote them as a backup app, which I think Christoph said is a pretty common strategy. And you'll see them advertised elsewhere, so people are clued into their real purpose.
So in summer 2016, Citizen Lab from the University of Toronto approached us with a surveillanceware that had been used to target a high-profile activist in the United Arab Emirates. The malware was aimed at iOS, and it used 3 zero-day exploits, one on mobile Safari, 2 on the iOS kernel to remotely jailbreak the device, and then install the actual surveillanceware. The malware had been created by a company called the NSO Group, and they refer to it as Pegasus. So NSO's business is what is generally called lawful intercept. Their customers are police forces, other law enforcement agencies, secret services, and so on. We know that the UAE, Mexico, and Panama are among their customers, but there are certainly more. The target market appears to be countries that are rich enough to afford the price tag of such a commercial professional surveillanceware, but not develop their own. The licensing cost per individual target of this is $25,000, as we know from some information that has leaked out. So Citizen Lab members have actually written an excellent series of articles on all of the known targets of Pegasus and how they were being targeted. So as soon as we had that in our hands, we knew there is probably an Android version of this, and so we went out hunting for it. We also figured, given the price tag, this is probably not very common. This is not a mass phenomenon. This is not going to be on millions of phones. But we have visibility into over 100 million devices and 50 million apps, and we did actually find some traces of this, some evidence, if you will. So we decided to get Google involved because they certainly have better visibility into the Android ecosystem than we did. And lo and behold, a couple of months later, Google got back to us with an actual 2014 version of Pegasus on Android. So we published a joint technical report with Google in April of this year on this surveillanceware. Handy for Google, Pegasus has a twin brother in Greek mythology who is called Chrysaor. Both of them were born from the Gorgon Medusa as Perseus chopped off her head. That's why she doesn't have a head in the middle there. The problem is nobody can pronounce that. So Google called it Chrysaor. We call it Pegasus on Android. But frankly, NSO had the best name for this thing, I think. They very conveniently left in their logging class when they shipped the app. And right there you can see they refer to it as Jigglypuff. What on earth is a Jigglypuff? I didn't know, but from the laughs, I can tell that probably some of you know.
So I think rather than talk about Pegasus implementation, we should probably just show you it in operation. Yeah, I think that's a good idea. So is this on the Chrysaor network?
Yeah, it should be.
You sure?
Oh, no, okay. So go off that one. Yeah, okay.
It's your laptop, so
yeah.
You can. So I'll talk a little bit about what you're going to see while Christoph goes to that. So we had a Pegasus app sample. We did not have a sample of the C2, and we're very unlikely to get one because NSO only sells to governments. So I wrote one to actually exercise the app. We've put a UI on it for demonstration purposes. And that's what you're going to see now.
I hope anyway.
We're making an effort here to show the phone screen.
Totally connected, but it doesn't see it. Oh, goodness. That is great.
Well, I think we're going to say you're out of luck with showing the phone. And
yeah.
Here, I got it. So what Christoph is doing is he's visiting a browser URL in the phone. So typically how Pegasus is configured is it's configured out of browser history. What it does on initial launch is it goes through browser history, parses out URLs looking for a magic string, and then it parses the parameters in this URL with a magic string. That's where it reads its configuration from, so it knows like which C2 to beacon out to, which SMS number to receive commands from. And it looks like he's got it deployed.
This thing actually reloads.
Yeah, so we should see the phone connect here in a second, and then we'll see it start to send data.
Can we force reload that?
Oh, yeah, there we go. It's too small, though. That's no good.
Wait, is that not it either?
That is it. Yeah, that's right. It's just off the screen. Here, hang on. I can.
Full screen. Draw the full screen and.
Yeah. Actually, I think that looks worse.
Yeah.
This isn't good.
Scroll over.
Yeah. There we go. This looks kind of bad, but I guess we'll make do.
There we go.
Okay, so here's some data we've exfiltrated, and I'm going to kick off a screenshot capture as well here. This looks a lot better not on a projector at a funny resolution. So here we can see we're getting data from third-party apps, and that's because Pegasus does rooting. It bundles the Frama root exploit kit, at least the sample we have. So we can look at, say, some email data here while we wait for a screenshot to come in. And this is Gmail data, and what it's doing is it chmod 777s the Gmail database and then just selects data out of it. So that's what your mails look like when Pegasus uploads them. Data is encrypted when it's sent to the C2, but the plain text is XML, and each data type is structured in a different way. Like we can see calendar data here. That's what that looks like. And we'll probably have a screenshot very shortly here. We'll take a look at Twitter too, or WhatsApp. So there's a WhatsApp message. Yeah, we were hoping to show a screenshot of the device, which takes about 2 minutes. Pegasus doesn't deal very well with a lower polling interval than that. There we go. So here's what a screenshot looks like. That's of Christoph's device. Thanks.